Okay, am I audible? So, if yes, then let's start today's class. So, today is week 4 of problem solving session of NPTEL. So, today we will be focusing on the theory of pseudo noise sequences. These past 3 weeks for spread spectrum, for past 3 weeks in Yeah. So as I was saying, for the past 3 weeks, we have been focusing on spread spectrum, direct sequence spread spectrum, and frequency hopping spread spectrum. So now, I think past 2 weeks, this third week class was postponed to 27th. So that class will happen on 27th of February. And this is the third class, not the fourth class, sorry. So today we will be focusing on the codes, pseudo noise sequence codes that make this possible, that make the PNC, that make the spread spectrum possible. So both at the heart of DS3 and frequency hopping spread spectrum is something called PN sequence generation. Without PN sequence generation, we cannot grade the random to the eavesdropper yet deterministic to the user model that we need. So let's go into the theory of PN sequence generation. I will share my screen. Uh, if the screen is not visible, please let me know. Yeah, I hope the screen is visible. So let me switch on one sec. Yeah. So today our topic is the theory of PN sequence and and we will then learn about few sequences which can be generated using the basic PN sequence, which are known as gold sequence and Kasami sequences. So first we will go through the basic PN sequence. So PN, at the heart of PN sequence is something called is not really okay. At the heart of PN sequence is something called a Galois field. So a Galois field is something that you have to uh, define something called a Galois field. So what is a Galois field? Let's go into the Galois field first. So to learn about PN sequence, we have to first know about Galois field, and we'll then switch to Galois field first. We will give a brief introduction, and then there is another week that is completely dedicated to Galois field, where we will go into Galois field in details. So wait 1 minute. Actually, these are all spread across multiple slides, so I have to find all of them. Yeah. So what is a Galois field? A Galois field is a field. What is a field? Field is a special kind of field. So what is a field? Field is an algebraic structure in which the operations, that is addition, subtraction, multiplication and division, are defined. Okay. So one such field is the usual arithmetic we do. That is one such kind of an example of a field. But this is abstract algebra. So basically the concept of multiplication, addition, division, subtraction, which we have done since childhood, they have been taken in an abstraction level. They are taken in a higher level of abstraction. So more precisely, a field is a set of two binary operators, set f with two binary operations, plus and multiplication, defined, in which the following hold. So plus has to there are two operations. One is a plus and one is a multiplication. So what are the properties for multiplication addition? So the addition properties are a1 through a4. For a field, it has to satisfy a1 through a4. One is a plus b plus c is equal to a plus b plus c. This is called associative law. Another is a plus b equal to b plus a, which is the commutative law, that you can interchange the operands. Then there is an identity element of addition. What is an identity element? Such that a plus that identity is equal to a. So what is that number which when you add, what is that element rather, not number, because this is abstract algebra. So what is that element which you add, we get a, this same element itself again, that is 0. And then there is the existence of an inverse. So as usual, the binary operation has to satisfy four properties. One is associative law, one is commutative law, one is existence of identity, one is existence of inverse. Similarly, multiplication also has to follow associative law, that is a into b into c is equal to a into b into c. So this is the associative law, and this is the associative law. And then there is the commutative law. The commutative law is a into b is equal to b into a. And then there is another, which is the identity law, that is there is an element of 1, element 1 not equal to 0. So what is this one element? How is this one element defined? This one element is a element that is not equal to the additive identity. So the multiplicative identity is separate from the additive identity by the fact that it is not equal to the multiplicative identity. So they are different elements. This 1 is not actually the number 1 that comes after 1, is after 0. So it is actually the multiplicative identity. So this one in another field where there maybe you don't have numbers, and the whole numbers, you have something else. There also this one will be the multiplicative identity. So one is not the number 1, it is the multiplicative identity. In case you define the arithmetic field over the natural numbers, then it is the one is the number 1. But this one is actually the multiplicative identity. And for any element a, there exists an element a inverse such that a into a inverse is equal to identity. That is the existence of inverse. And finally, after these 8 laws, there is a ninth law. This ninth law is the distributive law, which combines the addition and multiplication such that a dot b plus c is equal to a dot b plus a dot c. So if these 9 laws are satisfied, it is a field. Now, what is a finite field? The number of elements in a finite field must be, so what is the finite field? Finite field is a field in which, अरे यार, what is happening? Finite field is a field which has elements in the power of p. So power of p, where p is a prime number. Then for each prime power, q equal to p to the power n, there exists a field of order q and it is unique. So if there is a prime number p and p to the power n, if you define that, p to the power n will give rise to one field, finite field. So when we talk about this p prime, we use, in this context we usually talk about the prime 2. So 2 to the power n. So Galois field is basically the GF of 2 to the power n. So here mostly we are concerned with the GF of 2 to the power n. Elements of finite field 2 to the power n, where n is 0, 1, 2, 3, 4, etc. Okay. Uh, okay. We will now not go further into Galois field, and we will rather go into the code generation. PN sequence code generation. Galois field, this might be used later, so we will be keeping this in mind but not using this now. Wait, this actually it's not letting me download this, so that's why there is continuous obstructions are coming. So ha Arey. So to generate a Galois field, we must need a generate a field of a particular power. So this by generating a field of a particular power, we are basically relating this to the linear feedback shift register that we have read earlier. So yeah, so what is a linear feedback shift register? LFSR is the generation like chain of D flip-flops in which a particular combination of taps, say there are four, so a particular combination of taps of them will be combined in a XOR gate. So let's say and fed back. So let's say we take this and we take this and maybe we take this, but we don't take this, and we feed back the XOR to here. So this we assign 1, then this is x square, x cube. So we say that the generated polynomial of this PN sequence is 1 plus x cube, like that. Now usually when we generate generate the PN sequence from this linear feedback shift register, what we generate is M sequence. We generate something called M sequence, or maximal length sequence. So if we go into an example of an M sequence, yeah, so here we look at a example of a M sequence. So here we are taking the A0 or 1 and we are taking X, so it is just 1 plus X. Okay, so and then you finally take this and you give it to this X to final this expression, uh, sorry, this 1 plus x4. So finally you give it to this x and 1 and x, and you give it to x4. So finally you give it to 1 plus x4. The final polynomial is 1 plus x4. So a polynomial over the Galois field 2 can be associated with a linear feedback shift register. So the polynomial corresponding to figure 1 is x4 plus x plus 1. So a necessary condition for the sequence generated by LFSR to be maximal length is that its corresponding polynomial has to be primitive. It has to be primitive means it has to be irreducible. You cannot factor this polynomial into separate smaller polynomials. So this is one. uh, yeah. So yeah, this is what I was saying. So to generate a particular PN sequence over a polynomial, using a polynomial, the necessary condition for that to be maximal length is that the polynomial has to be primitive. That is, it has to have x4, that is it has to have x4 x, that is it has to have no factors, so it cannot be reduced into other smaller factors. So the maximal length sequences, if you generate like that, so basically you combine only those steps where you know you cannot further factorize the polynomials. 1 plus x4 cannot be further factorized, so we can say that the sequence that we have generated using this linear feedback shift register is a this maximal length sequence or M sequence. So what are the properties of M sequence? So the properties of M sequence that have been demonstrated are main balance property, run property, and correlation property. So balance property means that the occurrence of zeros and ones in these sequences must be approximately same. That is, the sequences that you will generate will have on an average the same number of zeros and ones. So more precisely, in a maximal length sequence of length 2 to the power n minus 1, there are 2 to the power n minus 1 ones and 2 to the power n minus 1 minus 1 zeros. So if you take 4 registers, so with 4 registers, how many bits you can generate? 2 to the power 4. How many sequences you can generate? 2 to the power 4 minus 1. So 2 to the power 4 minus 1, because 1 is trivial, 0 0 0 0. So you cannot take that, right? So the number of chips you can generate is 2 to the power 4 minus 1, that is 15. 15 chips you can generate, and in all of those 15 chips, you will see that 2 to the power 4 minus 2 to the power 4 minus 1 means 15 chips. Each of them will have 2 to the power whole n minus 1 ones and 2 to the power whole n minus 1 minus 1 zeros. That is, 2 to the power whole n minus 1 ones means 2 to the power 4 minus 1 in our example, 2 to the power 3, 8. 8 ones and 7 zeros. So if you generate a 15 length sequence, it will have 8 ones and 7 zeros, like that. So the number of ones equals the number of zeros plus the number of ones equals the number of zeros plus 1, since the state containing only zeros cannot happen. So the number of states that the number of ones that will be in this sequence will be equal to the number of zeros plus 1. Why? Because there we are explicitly excluding one state where all zeros occur. 0 0 0 0. Second is a run property. Run property means a subsequence which contains identical bits, that is consecutive ones or consecutive zeros. So like in the bit sequence 1 1 1 0, the 1 has a run of 3 because there are 3 consecutive ones. Whereas if you have a 1 1 0 0 0 0 0, so zeros now have a run of 4. So this is defined as run. So here if we take a even larger sequence of 15 length, say, 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 16. So here what is the run of 1 here? 3. There is a run 2. There are no other runs of 1. For 0 there is a run of 2, there is a run of 4, and then again there is a run of 2. So these are the runs. So the ones, one has a run of 2, then a run of 3, and zeros have a run of 2, then a run of 4, then a run of 2. So zeros have the maximum run that is that zeros have is 4, and the maximum run that ones have is 3. So a run is a subsequence of consecutive ones or consecutive 0 within the maximal length sequence or M sequence. The number of runs in the number of such sequences. The number of runs in the number of such subsequences. That is, the number of runs means the number of runs means the number of consecutive appearances. So how many runs are there for, like, in this sequence? Ones have how many runs? Ones have 3 runs. Sorry, ones have 2 runs. This one and this one. Ones have 2 runs. Zeros have 3 runs. So this is not a maximal length sequence. This is just a general sequence I have written from my mind. But in a maximal length sequence, one half of the runs are of length. So any run, the run can be of 1 or the run can be of 0. So we are not distinguishing between them. But one half of the runs, be it a run of ones or a run of zeros, one half of the runs will be of length 1. That is, they will be non-consecutive, 0 1 0 or 1 0 1, like that. The 0 in the middle of 1 0 1 does not have a run, right? It is means it has a run of 1. So half of the bits will be surrounded by non-identical bits. Half of the bits will be surrounded on both sides by non-identical bits. 1/4 of the runs are of length 2. So if there are, now let's consider the ones as runs also. So here is another run of 1, length 1. Here is a run of length 1. Here is a run of length 1. So there are how many runs here? Number of runs. Be it of 1, be it of 0. Let's not distinguish. Number of runs is, there is 1 run here, 1 run here, 1 run here, 3, 4, 5, 6, 7, 8. There are 8 runs. Out of which how many are of length 1? 3 are of length 1. So this is not MLS, not maximal length sequence. Means the polynomial with which this was generated is not a primitive polynomial. Okay. So it is not a primitive polynomial. Thus, this is not maximal length sequence or not M sequence, because the number of runs which are of length 1 are 3. But in a maximal length sequence, the number of runs which are of length 1 should be 4, because the total number of runs is 8. So next, how many runs are of length 2? 1, 2, 3. 3 runs are of length 2. But how many runs should have been of length 2? Anyone? If this sequence was a maximal length sequence, how many runs should have been of length 2? A quarter of the runs are of length 2.
One
So
quarter of the run.
yes, so 2, only 2 runs should be of length 2. So this is not a valid MLS again. And then we go on and on. 1/8 of the runs will be of length 3. So 1/8 means only there should be one run of length 3. And that property I think is satisfied. There is only one run of length 3. But there is a run of length 4, which should not happen. Why? Because the next is 1/16th of the runs are of length 4. But 1/16th is 1/16th of a sequence, that is 1/16th of the runs. But there are only 8 runs. So 1/16th of the runs does not exist. So it has to have 1/2 of the runs of length 1, 1/4 of the runs of length 2, and 1/8 of the runs of length 3. Okay. So this is the run property of maximal length sequence. And third is the autocorrelation function. property. So the correlation property. So if you take the autocorrelation of a of a maximal length sequence, you will get the delta function. That is, if you take the autocorrelation, but that delta is offset by -1 by n. That is, it is not exactly delta, but what I mean, what they mean to say is there will be a spike at 0. So there will be a spike at 0, and then it will be flat all around it. So it's not exactly an impulse, it is basically a my screen is visible, right? This is will be a uh, what happened, huh? Will be a yeah, where was I? 1 minute. Yeah, so the correlation will look like something like this. It will be flat all around. Sorry, this is not flat. So again it is this. Yeah, so at 0 it will have a peak and flat all around. So this is the correlation of a MLS. Autocorrelation. So what does that mean? That if you delay the sequence, it will have zero correlation with itself. So it means the sequences, this highlights a disadvantage of MLS, that it has to be synchronized perfectly. If you miss the synchronization by even 1 bit, your code will be completely off. The received and the transmitted, if they are desynchronized by 1 bit, the correlation will be 0. They will be absolutely uncorrelated. But if two things have the same information, they cannot be uncorrelated, right? So that is the disadvantage of maximal length sequences. Yeah. So M sequence or binary maximal length shift register sequence are generated using linear feedback shift register and linear generator polynomial of degree m. Yeah, if any one of the taps of this is open, then sorry, the switch is closed, then it is considered 1. Otherwise the tap is considered to be 0. So it is g1x plus g2x square plus g3x cube, like that. If they are 0, so if you close them and you close them, you close some of them and you open some of them, and then basically these plus are basically XORs. So finally you XOR them and you get the result. And the rightmost feedback shift register, that corresponds to this term. So the rightmost is not the highest power, the rightmost is the lowest power, x to the power 0, and as we go left the power increases. So here we can see that here how many are open. This one is open, this one is open, this one is open. This one is x to the power 0, so it is 1. This one is x to the power 1, means x. This is x square, we skip. This is x cube, we skip. This is x4, we take. So 1 plus x4. Is this clear? Is the principle of generator polynomial clear? Please respond. Okay, I am assuming it is clear. So basically whatever is connected to the XOR gate, that is assumed to be open, and from the left to right the power increases. We take the corresponding powers, we add them to get the generator polynomial. And if that generator polynomial is not factorizable, then the sequence is a maximal length sequence, else it is not. Yeah. So here you can see one example of a maximal sequence generation, and the polynomial is x5 plus x4 plus x square plus x plus 1. So you take x1 x x square, x cube you miss, you take x4 x5. So see, this is raised, 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 except for x cube, all are raised. So it is basically 1 through x to the power 5 except x cube. So 1 plus x square plus x4 plus x5, that is the generator polynomial. Now this polynomial can be shown to be not factorizable. This is not factorizable. So this is a maximal length sequence. Now when you start at the first pulse, you have to make sure that at the first pulse your registers are not in the dead state. What is the dead state? What is the dead state? Anyone? Which state is called the dead state? Just write in the chat box or I open your mic. We have to show some interaction, or else this is an interactive class, right? Or else even I will be in trouble. So anyone, any interaction? So a dead state is basically all zeros. All zeros means dead state. So when you put all zeros, then after that in the next pulse also whatever combination you use, it is all zeros. Again it is all zeros. Why? You simply put here only in this sequence. If you put zeros, all zeros, here 0, here 0, all of the coefficients are zeros, then it will always be 0. But if you start from say 1 1 1 1 1, not necessarily 1 1 1 1 1, you can start from any state except for the dead state. So here they are starting from all ones. So when you are doing all ones and then they are applying a mask, and you from that one all ones you get the next state to be 0 1 1 1 1, then 1 0 triple 1, like that the register states are switching. And after 30 31 states, 0 to 30, so 31 states, it again starts at 1 1 1 1. So it is periodic after 31 states. Why 31? Because there are 5 register. 5 register means 32 states. So 5 register implies GF 2 to the power 5 implies 32 states implies usable 31 states. Usable 31 states. One dead state. So 31 states. So you will see after 31 it will periodically repeat. So the period, we can from this what we can say, that the period of an M sequence is if there are n registers. So here basically from we are linking the polynomial generation, the bitwise generation, and the hardware generation, all three together. If there are n registers, then 2 to the power n minus 1 states, then period of m sequence, period of the maximal length sequence is equal to 2 to the power n minus 1 clock pulse. So 2 to the power n minus 1, the sequence will repeat itself after 2 to the power n minus 1 clock pulses. So a binary linear shift register sequence that has a period n equal to 2 to the power n minus 1. So the number of shift register is also the degree of the polynomial. You know what is the degree of polynomial? Degree means the maximum power. So the number of states that you have in the register is also the degree of the polynomial of the generator polynomial of that sequence. Now for that sequence to be maximal length sequence, the generator polynomial has to be primitive. We have discussed that earlier. Now see, gx equal to x to the power 5 plus x4 plus x squared plus x plus 1. That is the polynomial that we have discussed earlier. Again it has gone behind a paywall. This is so irritating. So this is, we have discussed this polynomial. This polynomial is all powers except x cube. Now all powers except x cube is not factorizable. So how do you check for factorizability? You divide by x to the power n plus 1. If there is a factor, then if there is a factor such that the smallest n is not 2 to the power m minus 1, that is x to the power n plus 1, you start from x plus 1. So and you go up to n equal to 2 to the power m minus 1, right? So x to the power, say here it is x to the power 5 plus x4 plus x square. So you start from x plus 1, then you go to x square plus 1, and you keep on dividing, first by x plus 1, first by x square plus 1, then by x square plus 1. Whenever you reach a factorization, that is it is divisible, the polynomial is divisible, then it is a generated, it is not a primitive polynomial. Whereas if you exhaust, you can maximum go to 2 to the power m minus 1, right? So till you go to 2 to the power m minus 1, if you exhaust all your attempts, x plus 1, x square plus 1, x cube plus 1, all your attempts till 2 to the power m minus 1, and still you are not able to divide it perfectly, divide the polynomial perfectly, then it is primitive. So x5 plus x4 plus x square plus x plus 1 is primitive. On the other hand, if you include x cube, then x5 plus x4 plus x3 plus x2 plus x plus 1, this is not primitive, because this is not primitive because you can divide by x plus 1, x to the power 6 plus 1. So if you divide by x to the power 6 plus 1, then you can divide it. Means you can divide this polynomial by x to the power 6 plus 1, you will get x plus 1, like that. So basically it is factorizable. So x to the power 6 plus 1 is equal to x plus 1 into this x5, x4, x3, x square, x plus 1. Now this x to the power 6 plus 1, basically you have gone till 6. Sorry, I was wrong. হ্যালো, হ্যাঁ 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 আজকে চলে গেছি আমরা ওই চেক আপের জন্য। কালকে বিকেল সন্ধ্যেবেলা আসবো স্টিল এক্সপ্রেসে। হ্যাঁ হ্যাঁ। আচ্ছা ঠিক আছে ঠিক আছে, কোনো ব্যাপার না। আমরা আমাদের পার্টটায় তালা দিয়ে দিয়েছি। আর কাল সন্ধ্যেবেলা আমরা 7টা নাগাদ আসবো, 7টা নাগাদ তো থাকবেন তখন খুলে দেবেন। হ্যাঁ হ্যাঁ হ্যাঁ, ওই 7টার দিকে ওই স্টিল এক্সপ্রেসে যেমন আসে 7টা 7:30। হ্যাঁ ঠিক আছে, ওকে। Okay. Apologies for the phone call. So yeah, where were we? So we can divide by x to the power 6 plus 1. So the smallest n is 6, and 6 is lesser than 2 to the power m minus 1, which is 31. So we started from x plus 1, then x plus 1, x squared plus 1, x cubed plus 1, like that we went. When we reached x to the power 6 plus 1, we saw that it is factorizable. So we say that this polynomial is not primitive. So the number of primitive polynomial, the number of this primitive polynomial is 1 by m phi 2 to the power m minus 1, where phi is defined as this product 1 minus 1 by p multiplied how many times phi n. So the number of primitive polynomial of degree m is degree, that is the number of shift registers, so is equal to 1 by m phi 2 to the power m minus 1, where phi is a function defined as n into product of 1 minus 1 by p's. And what is p value? P is all the over all the distinct prime divisors of n. So all the distinct prime divisors of n is 2 to the power m minus 1. So I think that is yeah, for m equal to 4, for m equal to 4. So for m equal to 4, by this formula, how many primitive polynomials are possible? 1 by 4 phi 2 to the power 4 minus 1. So phi of 15. What is phi of 15? Phi of 15 is basically 15 into 1 minus 1 by all the prime factors. So 1 minus 1 by 3, 1 minus 1 by 5, because 15 has two prime factors, 3 and 5. So 1 by 4 into 1 minus 1 by 3 into 1 minus 1 by 5. So you end up with 1 minute. I will just unlock this document, or else every 2 seconds it is. I will just unlock this document. Give me 2 minutes, or else every 2 seconds this advertisement will come. Tarika. Oof, it is not. Yeah. uh, yeah, now I have downloaded it. Now I won't have any problem. Yeah. So this linear generator polynomial. So where were we? We were discussing, I think, m. Huh? So am a 1 by m into, so if for m equal to 4, there are two polynomials. And what are those two distinct primitive polynomials? One is 1 0 0 0 1 1, and another is 1 1 0 0 1. But you will say these are bits, these are not polynomials. So how to convert them to polynomial? Simple, you just take the rightmost and make it 1, and from there you add 1 plus skip x square, x cube plus x4, and this is 1 plus x plus x to the power skip square, skip cube, skip 4, skip 5, 1 plus x plus x5. So the two polynomials are, one is 1 plus x plus x5, and another is 1 plus x cube x4. Yeah. So now for extensive tables of primitive polynomials, you have to find in internet. Now, what are the property of maximal length sequence? That one is the shift property. That is, a cyclic shift of an m sequence is also an m sequence. So if you shift the m sequence cyclically, that is, the rightmost bit must come back to the left, and the left like that in a cycle. If you shift, how many times you shift, you will always end up with an m sequence. So that is the first property, this one. Next is the recurrence property. Any m sequence in Sm satisfies the recurrence condition. This recurrence condition, I think, is not needed. Window property, these are not needed. But one more ones than zeros. This is the, what is this called? This is called the balance property. This is called the balance property that we have already discussed earlier, right? These are the balance property. And then there is addition property, and then there is the autocorrelation property that we have, and then there is the run property. Run property we have already discussed, that there will be one half of the length run, one half of runs of length 1, 1/4 of runs of length 2, 1/8 of runs of length 3, and so on. And the rest of them are not needed. So M sequences in summary have a thumbtack autocorrelation function. Thumbtack autocorrelation means flat, then it will go up, then it will again be flat. This is a thumbtack, or this is called a thumbtack autocorrelation, or you can say it's an impulsive autocorrelation, like this. This, then it will rise like this, then it will fall again, and then this. Best possible periodic autocorrelation. So it will have the best possible autocorrelation, and but what is the difference? The number of such sequences is small. The number of such sequences is small, as defined earlier by the prime factorization theorem that we have seen. Now, the M sequence, and but what are the disadvantage? The main disadvantage of M sequence is some M sequence pairs have large cross correlation value. When you are saying, what is the purpose of spread spectrum? One purpose of spread spectrum is privacy, of course. Another purpose of spread spectrum is to accommodate as many users possible. So you have to accommodate as many users possible in a small area. Okay, so you have to accommodate as many users as possible in a small area, small area of I mean bandwidth. Okay, not small, rather, or you have already spreaded it, so not small, but you have to accommodate a large number of users in a limited bandwidth, or else you cannot justify the increase in bandwidth. So the sum of these m sequence pairs will have large cross correlation value. So if you assign one of the chips in this sequence to one user, another chip in this sequence to another user, and if they have a large cross correlation, there will be a large crosstalk. So this will lead to problems with crosstalk. Okay, so this will lead to problems of crosstalk. And this periodic cross correlation is just the the two product of the two, but you have to product of the two sequence chips, but you have to shift them, of course. One, you have to shift one of them, and then this that shift will vary. So ui v nu n plus I. So you have to multiply them, shift and add, like that. Like where you get autocorrelation, you will get cross correlation. Okay, now we come to the concept of gold sequences. So I think you can take 2 minutes of break. I will just go to the washroom. So we'll join back after 2 minutes, and then we will go to gold sequence and Kasami sequence. হ্যাঁ, তালা দিয়েছি। এটা আসলে লাইভ ক্লাস হয় তো পুরো ইন্ডিয়া থেকে লোকজন। আর তো তার জন্য আরে আমি তোদের মধ্যে যাচ্ছিলাম ছিল শুরু করা এক রোল করে তো দুবার শুরু করতে বলেছে না না দাঁড়া না অ্যাড্রেসটা হলো আমি করেছি ও তো করে গেছে Yeah, so let's resume. So what is a preferred pair? Any pair of sequence, M sequence, that is any pair of maximal length sequence that have the same period n can be related, by, can be said to be a preferred pair. So basically, two maximal sequences, they have to be related and they have to satisfy certain conditions. So what I think this definition is not that good. I will go to the Wikipedia. I think there you will get a better definition. Prefer, here it is not written well. Preferred pair of M sequence. So yeah, a preferred pair of M sequence consists of two sequences U and V of length n equal to 2 to the power n minus 1, 2 to the power n minus 1, n equal to n not equal to 0 mod 4, that is n is not divisible by 4, which have a specific low cross correlation value of 2 to the power n plus 2 by 2 plus 1, 2 to the power ceiling n plus 2 by 2 plus 1. So basically it has been, these are all empirical findings, like they are preferred pair basically are two sequences which have a relation between them. They have to have the same periods, and if you take n equal to n not equal to 0 mod 4, in that cases it has been shown that there is a low cross correlation value. So basically these are found by mostly by trial and error. So this preferred pair of sequences is a preferred pair of sequence is a specific kind of M sequence. See, M sequence already has good autocorrelation. So the preferred pair of M sequences will have very good cross correlation also. So these preferred pairs have very good cross correlation properties. So M is not equal to 0 mod 4. That is one of the main criteria of a preferred pair, that the length has to be not divisible by 4. That is M is odd or M is a factor of 2. That is it does not have to be a leap number. It has to be a non-leap number. Now once that is satisfied, once the degree of the maximal length sequence is not leap, that is not 4, 8, 16, something like that, then it can be shown that these M sequences will have very minimal cross correlation value. Now gold length sequences are basically, gold here is a name of a scientist, not gold as in literal gold. So gold sequences of length then can be constructed from a preferred pair. So you take two maximal length sequences of the same length and same period and not leap, that is not mod 4, then you will have a preferred pair. And when you take a preferred pair and you combine them in some specific fashion, you get a gold sequence. And what is that specific fashion, that we will come to later. But a preferred pair of M, first we will say that a preferred pair of M sequences, say x and y, has a 3-valued cross correlation function. So theta x comma y, that is the cross correlation function, will be minus 1 or minus Tm or Tm minus 2, where Tm is this 1 plus 2 to the power ceiling n plus 2 by 2. So this is shown to be a very low value of cross correlation compared to other pairs. That's why we use preferred pair. The set of gold sequence includes the preferred pair of M sequences x and y and the mod 2 sums of x and cyclic shifts of y. So what gold sequence is constructed basically by modulo 2 sum, that is XOR. So you take this modulo 2 sum is basically uh, where did I keep my pencil? Array. Got it. So this is XOR. Yeah. Uh, so this is basically XOR. So if you have a preferred pair sequence x and y, you take x, you take XOR y, you take x, you take y, you take XOR y, then you take XOR one cyclical shifted y. T inverse y means one cyclical shifted y. That is, if you say have one sequence as then another is x XOR two cyclical shifted y, then up to n minus 1, where n is the period, n minus 1 cyclical shifted y. So this is the set of gold sequences. The maximum correlation magnitude for any two gold sequence in the same set is equal to the constant Tn. So if you take any two sequences from these sequences, set of sequences, you will always get a maximum correlation of Tn. So it is some kind of a correlation floor. So you will not get more correlation than that. So that is good. That is like a good value, as low value. So that is why gold sequences are preferred to minimize cross correlation. So let's say you have a gold sequence, a maximal length sequence like 110 10 1. I don't think this is maximal. I am just giving an example. This may not be maximal. So this is a 6 length sequence. So it has to be non-modulo 4. So 1101 cannot give you gold sequence because 1101 won't have a preferred pair. It has to be non-modulo 4. So this cannot give you no gold sequence. Why not modulo 4? That you have to then find the original paper by Gold and Kasami, and there you will find the derivation, but that is way beyond the scope of our text. So now this is 101, say 010, like that, something like that. So this is one sequence, another sequence. The gold set will be constructed by this, then you take the XOR. So x XOR y, this is x, this is y. Now you take x XOR y. 1 XOR 1 or 1 plus 1 modulo 2, that is 0. Then 1 XOR 0 is 1. 0 XOR 1 is 0. 1 XOR 0 is 1. 0 XOR 0, 0 XOR 1 is 0. 1 XOR 1 is 0. So this is one sequence. Another sequence. Now these are not maximal length sequence. I am not guaranteeing that. I am just saying if they were maximal length sequence. Because to generate the maximal length sequence, now I have to think. I have to design the runs like that. So I am not doing that. I am just saying, like, if they were maximal length sequence, you will generate the gold set like this. So next you have to give XOR 1 shifted. So you can say T inverse Y. Or some people denote as Z inverse Y. Z inverse means 1 delay, right? So Z inverse Y, some people delay. Some textbooks use Z inverse Y. So this will be basically the XOR of 110 101, and as you do one cyclical shift of 101010, that is one cyclical shift of Y, what will you get? 0, the rightmost 0 will come to left, then you will have 10101, 1s or 0 is 1, then 1s or 1 is 0, 0s or 0 is 0, 1s or 1 is 0, 0s or 0 is 0, 1s or 1 is 0, 1 0 1 is 0. So this is 1 0 0 0 0 0. Like that you will get another is x XOR z to the power minus 2y, that is 2 delayed. Then you have to do 1 1 0, this is x, this is z inverse y, and this is x, this is z to the power minus 2y. So it is 1 1 0 1 0 1, x is unchanged, 1 1 0 1 0 1, y is the, you have to shift by 2. So basically you shift, instead of shifting this by 2, what I will do is I will shift this by 1, same thing. So if I shift this by 1, the rightmost one will come here, then you shift all the bits to 1 bit right, 1 0 1 0 1 0. So 1s or 0 is 1, 0s or 1 is 1, 1s or 0 is 1, 0s or 1 is 1, 1s or 0 is 1. So, and 1s or 1 is 0. So it is just the opposite, 0 and then all ones. Like that you generate the gold set. If you are given two maximal length sequences, this is how you generate the gold set. I hope this is clear. So here also they have given one gold set generation. So for m equal to 3, for 3 degree polynomial, the number of m sequences is 1/3 of 5 7. 5 7, how many prime factors does 7 have? 7 has only one prime factor, that is 7, apart from 1. So it has only one prime factor, 7, because it is a prime number. So 1 minus 1 by 7. So 1 by 3 into 1 minus 1 by 7. So 6 by 7. In, so 1 by 3 into 7 into 1 minus 1 by 7. This will be the number of m maximal length sequences for degree 3. So 1 by 3 into 7 into 6 by 7. You cancel everything out, you get 2. So there are only 2 m sequences, and each of them will be of length 2 to the power n minus 1, of course, 7. So what are those sequences? By trial and error you find the sequences are this: 1 0 0 1 0 1 1 1 0 0 1 1 1 0. So this you have to find by trial and error. Basically you have to find all the generator polynomials, then factorize each one of them to find which are primitive. The ones which are primitive will give you maximal length sequences. So the two maximal length sequences are this. Now you just, like I have shown you, you just do XORs. So first you do x, first you put x, then you put y, then you put XOR y, then XOR z inverse y, then XOR z to the power minus 2y. How many you will go till? To the power n minus 1. So z to the power, how many delays? Z to the power minus 1, z to the power minus 2, like that. How many delays you will give? Up to z to the power minus 7 minus 1. That is z to the power minus 6. So up to 6 delays you will add. Okay. So z to the power minus 1, 2, 3, 4, 5, 6. So there are 6 delayed sequences. And then there is x, there is y, there is XOR y. So there are 3 plus 6, 9 gold sequences. And the 9 gold sequences are these. So this forms a gold set. In cross correlation between any two member of this gold set will be less than that Tn constant, that floor. Okay. So the cross correlation will be 1, minus 1, minus 5 or 3. So it will maximum go to 5. The magnitude of cross correlation will maximum go to 5. Not more than that. Now we go to Kasami sequences. So Kasami sequences are obtained by decimating the M sequence X and performing mod to addition on cyclically shifted sequences. So what is decimation? Decimation means you delete every like second or every third or every fourth, however you want, bit. So if you have say four bits and you do a decimation by 2, so you delete every second bit. So 1011, you delete 0, you delete 1, so you will get 1011, you delete the 0 and the last 1, you get 11 as a result. So that is decimation by 2. So decimation basically means like in Roman times, the as a punishment for the enemy soldiers when they were captured, what they did is that they like the captors, those who have won, they used to kill every 10th enemy soldier. So if there are 100 soldiers in a battalion, they will kill every 10th and spare the rest 90. So that's how that was decimation. So by 10. Now here decimation is a general term. It means dividing, means deleting every certain, after every certain period. So decimation by 2 means deleting every second. Decimation by 3 means deleting every third element. So here after you do a decimation and then you get a y. So you have a original sequence X, you perform a decimation and you get a sequence Y. Then the small set of Kasami sequences is given by X, XOR Y, XOR Z inverse Y, XOR Z to the power minus 2Y, like that till XOR Z to the power minus 2 to the power M by 2 minus 2Y, like that. So you will do decimation and you will get X. And you will do decimation by how much? You will do decimation by say 2 to the power m by 2 plus 1. So now 2 to the power m by 2 plus 1. So the you will decimate, do decimation such that the length is 2 to the power m by 2 plus 1. Okay. So the total number of sequences in this set will be 2 to the power m by 2. Yeah, you are doing from 2 to the power till 2 to the power m by 2 minus 2. So how many powers? 2 to the power m by 2 minus 2 plus 1, you have x or y. So 2 to the power m by 2 minus 1 plus you have 1 as x. So 2 to the power m by 2. Here in gold sequence, y was the preferred pair of x. In Kasami sequence, y is the decimated version of x. That is the difference between gold and Kasami. Okay. So you note it down for future reference. This is important, that in gold sequence, x and y are independent sequence, basically are independent preferred pair sequences. So they are generated independently, but they must be preferred pair, are independently generated preferred pair sequence. You see in gold sequence the two sequences will have the same length because they are preferred pair. But in Kasami sequence, one of them will have a smaller period because why? They got decimated. So x and y are generated preferred pair sequence. In Kasami, y is the decimated version of x. Now, so this clears gold and Kasami. Now, this set of Kasami sequences was said to be the small set of Kasami sequences. And then there is another called large sequence of Kasami large set of Kasami sequence. Now large set of Kasami sequence consists of sequences of period 2 to the power n minus 1, which is natural, the maximal length sequences of M, and contains both the gold sequence and the small set Kasami sequence. So large set of Kasami sequence means small set of Kasami sequence plus the original sequences plus gold set. Okay, so you take all of the sequences that you have generated till now, you club them together to get large set of Kasami sequences. So here there is a example of a generation of a small set of Kasami sequence. Large set you can generate from here by combining the small set and the gold set. So small set, so large set equal to gold set plus small set. In simple terms, there is of course the sequence itself, but if we neglect that for now, the sequence itself also has to be included. Actually the sequence itself is included in gold set, so we can say that large Kasami set is equal to gold set plus small Kasami set. Now the so you decimate x by sm and you get, so the primitive polynomial, so Kasami sequence of m equal to 4. So for m equal to 4 there is a primitive polynomial x4 plus x plus 1 and corresponding bit is this. Now the sm is obtained by sm is obtained by 2 to the power m by 2 plus 1, doing 2 to the power m by 2 plus 1, so is equal to 5. This sm is your decimating factor. This is your decimating factor. Yeah, so 5 is your decimating factor, so you have to decimate this sequence by 5. So if you decimate this sequence by 5, wait a minute. Okay, we have to do cyclic decimation. So we have to decimate by 5, and if we decimate by 5, of course we cannot generate the same length because, oops, 1 minute. Yeah, so if we generate decimate by 5, of course we cannot generate the same length to XOR because XOR operation will not happen. So we have to artificially increase the length of the decimation. So we have to artificially increase the length of the decimation. We take the first one, okay, then decimation by 5, this is for, so 2, 3, 4, 5. So yeah, sorry, not this one, this is 1, 1, 2, 3, 4, 5. So you take 0. Yeah, you delete this 0. So you have done one decimation. Okay. Next, I think no. Wait. I think I'm doing it wrong. 1 0 0 0 1 0 0. Yeah, 1 0 0 1 1 0 1 0 1 0 1 1. So decimation by 5. So you start here 1 2 3 4 5. You delete this. You delete this. Next, 1 2 3 4 5. You delete this. Then 1 uh, sorry, we are not deleting here. We the this decimation does not work like that. Sorry, I got it all wrong. My apologies. Basically, instead of deleting, what we will do is we are deleting in one way, but we are taking the deleted sequence instead of taking the whole remainder sequence. So 1 0 0 0 1 0 0 1 1 0 1 0 triple 1. So we sample every fifth. So 1 2 3 4 5. So we take 1 1 2 3 4 5. So we take 0. Then 1 2 3 4 5. We take 1. Now we have to repeat this till we have the same length as x. So the next is 1 2 3 4 5. So another one. Then again we will see that we will get 101 only, because we are landing at the same thing. 1 2 3 4 5. So again 0. Then from this 0, 1 2 3 4 5. Again this one. So we will be always choosing this one, this 0, and this uh sorry, this one, this 0, and 2 3 this one. So we will be always end up choosing 1 0 1. So we will repeat again 1 0 1. We will repeat again 1 0 1. We will repeat again 1 0 1. Okay. Because we are doing a cyclic decimation, so we will be always ending up at the same spot. So we take one cycle, we make one cycle, and then we will end up again at the same samples. So we will always be choosing the 5th, 10th, and 15th bit, because we are selecting every 5th. So here we are not deleting every 5th, as is implied by the original meaning of the word decimation. Instead of deleting every 5th, we are selecting every 5th. Okay. So we will end up with 101, 101, 101, 101. But here this has a very large period. What was the period? The period was 15, 2 to the power m minus 1. This one has a period of 3. See, here the period is 15, but it got decimated by the decimation factor of 5. So the new period is period equal to 3. So when you decimate by a certain factor, the period reduces that much. Okay. So now the period is 3. So the next this y, the period of y is 3. So the number of Kasami sequence will be 2 to the power m by 2 or 4. And the Kasami sequences will be given by, now you have to do this sequence, you have yx, and this sequence you have y. So now you again do x, xor y, then this xor z inverse y, xor z minus 2y, like that, and you generate all the Kasami sequences. And the Kasami sequence will also have -1, -5 or 3. These are the gold and Kasami codes. So yeah, we will just take up, I think most problems are already, assignments are released, I think answers are also released, so we will be not going into problems much, because I think the problems have already been, the assignments have already been released, so there is nothing much more for me to discuss in the problems. Let's still open it. If you have any doubt in the problem, you can ask. Yeah. So here you see the maximal length sequence generated by a shift register of length n equal to 10 is used in generation of Kasami code. Of course, n equal to 10 is way too large for hand generating Kasami codes. So you will be not asked to hand generate Kasami codes like that. But instead, you will be given MATLAB assignments to generate Kasami codes of practical lengths, because by hand we can generate 3 or 4 length. After that it becomes untenable. The magnitude of the worst case cross correlation for small Kasami sequences, yeah, the small Kasami sequence takes on these values. So the small Kasami sequence cross correlation values. So cross correlation, it takes on three values: -1 by n, minus Sn by n. What is Sn? Sn is the decimation factor. This is the decimation factor. And another it takes value it takes is 1 by n Sn minus 2. These are the three cross correlation values it takes. Okay. So if 1 by n, so we have to find the decimating factor. What is the decimating factor? The decimating factor is 2 to the power m by 2 plus 1. So here m is given to be 10. So 2 to the power 10 by 2 plus 1. So 2 to the power 5 plus 1. So 33. The decimating factor is 33. And what is n? N is the length of the m sequence, maximal length sequence. So 2 to the power n minus 1. So rather 2 to the power m minus 1. So 2 to the power 10 minus 1. So this is 1023. So the values of correlation will be, either it will be minus 1 by 1023, or it will be minus 33 by 1023, or it will be minus 1 by 1023 into 33 minus 2, so 31. 31 by 1023. So 33 1 by 1023. So worst case means largest magnitude. Here the negative sign is inconsequential, because we are seeing what is correlation. Correlation is similarity. Whether the similarity is positive or negative is immaterial. The similarity magnitude matters. So 33 by 1023 is the worst case. This is the worst. So 33 by 23, what 1023 is your worst case cross correlation. So what is 33 by 1023? If you do calculation, let me check on my phone. 33 by 1023 is 33 by 1023 is 0.032. So the correct answer is 0.032. Simple. For large Kasami sequence, again the cross correlation values, these you have to by heart, because the derivations of these are beyond our scope. So again it is n is 1023, we have discussed. So it is minus 1 by 1023. This will of course be the best case. This is the case for, this is like the uh, max m sequence like cross correlation. So it is like the m sequence autocorrelation. That was the best case. So it is m sequence autocorrelation like. So this is like the best case you can get. 1 by n. It is very small. But there are other values. One is 1 by 1023 minus 1 plus minus 2 to the power n by 2. So 2 to the power 10 by 2. So মা কি হয়েছে? শুয়েছিলে, শুয়ে থাকো না। আচ্ছা আমি 5 মিনিটে খালি করে দিচ্ছি। হ্যাঁ, তো ওকে, সো 1 বাই 1023 বসো, চেয়ারটায় বসো, চেয়ারটায় বসো। হ্যাঁ, সো 1 বাই 1023 minus 1 plus minus 32. So minus 33 or minus 30 or plus 31. So minus 33 is of course the worst case. So we will take minus 33, 1023. And another here is minus 1 plus minus 2 to the power n by 2. So again 32 plus 1. So minus 1 plus minus 33. That is either 32 or 34. So who is joining now? Class is nearly over. Oh, okay, okay. Yeah, so this is 33 or so these are 32, 34. So this will take 33, 31. This will take 32, 34. So what is the worst value? 34. So the worst case cross correlation is 34 by 1023. This is the worst of them all. So 34 by 1023 is 0.033. So it is 0.033. Okay. So yeah, rest of the code, rest of the problems you will get, you have already got the solution. So I think there is not much to discuss. So yeah, we will be finishing our class here only. If you don't have any doubts, do you have any doubts? If not, then we will be finishing the class here only. Thank you, have a nice day.